Okay, everyone. Sorry to be all scruffed up looking, but I wanted to get a lecture in today. So here we go. We're going to start Unit 3 today, which is on carboxylic acids, esters, and lipids. The chemistry of lipids is the chemistry of carboxylic acids and esters. Okay, so what we're going to do is now zoom over to, all right, these are very ubiquitous. Um, in our biochemical world, particularly. Obviously, inorganic acids are very common as well, but organic acids are actually more common than inorganic acids. Okay, now we talked about the carboxylic acid carbonyl, and that's this guy here. Now, when we add an OH to that, it takes on a lot of different properties. And they've been a very old studied group. So there's a lot of common names. So we're going to learn the common names. We're also going to learn the official organic names and also the official biochemical names. So there are three groups we're going to be learning. Okay, so these are probably the um, most common um, uh, acids you probably are familiar with, not necessarily knowing their name though. Formic acid is an acid, interestingly, it's the simplest acid. It just has the acidic group, the organic acidic group, COOH, and it only has an H there. Now, this is interesting because it was named after ants. Forma is Latin for ant, and it has to do with the way um, the when a red ant stings you, they inject formic acid into you, and that's how it was connected up. Acetic acid, good old vinegar, propionic acid. You've probably not heard of that as propionic acid necessarily. It's used as a mold inhibitor. Butyric acid is interesting. It's a very stinky acid. I mean, very. It smells like cow patties, and that's where um, uh, people get its name. But if you bond that with an alcohol, it becomes very non odoriferous. And here's some other ones: citric acid you've heard of, lactic acid you've heard of. These probably not necessarily you've heard of before. Oxalic acid is becoming more and more prevalent now because the salt of this oxalic acid is called oxalates and is very prevalent in things like spinach. Um, and it is not very good for you. So the best thing when you cook spinach is to get rid of the water you cook it in because that's where all the oxalates tend to be. Fatty acids are an acidic group with a very long chain. Um, it's they call it hydrophobic because it does not like water, nonpolar, as opposed to the other end of the fatty acid, which is very polar, hydrophilic. So we have a non-water and a water-loving group on the same molecule. Makes some very interesting chemistry. Okay, so the IUPAC names for these tend to be pretty easy. You've got the normal three parts. This is backbone. This is the functional group, and these are branches. Okay, so if we look at this guy, for example, we've got the backbone is 4. So it's going to be a buta. And because it's an acid, it's an oic acid. So it's a butanoic acid, and it's got a branch on carbon number 3. So it's 3-bromobutanoic acid. Now, the aromatics, of course, always differ from the non-aromatics, the aliphatics. Okay, so if we have a aromatic, meaning benzene, as an acid, it's called benzoic acid. And it's got a branch on carbon 3 and 4. So it's 3,4 dimethyl. Benzoic acid. Okay, now this COOH is extremely polar. In fact, it's so polar that when acids are together, they form something called a dimer. And that's where they bond big time. These guys are going to be the most strongest polar molecules. Hence, it's going to be the highest boiling points. And that's highest boiling points we've studied so far. And you can see equivalent molecular weights. We can see the boiling points differ dramatically. So this is that graph I always show. And here we have the carboxylic acids up top here. Okay, because the COOH is highly polar, it's very soluble in water. Very soluble in water. Unless it's got a fatty acid chain of aliphatic groups that are really, really long that overcomes the polar end acid. So again, we're looking at, this is C6, making the difference between soluble and insoluble. In other words, this highly aliphatic or non-polar end overcomes this very, very polar COOH. Okay, because they're an acid that is defined as disassociating an H plus, okay? In this case, the H plus is coming off the carboxylic acid group, and this shows it bonding with water, forming hydronium ion, but if we take it in its simplest state, it's going to be an H plus. So under high pH conditions, nothing happens. Under low pH conditions, or alkaline or basic conditions, the H comes off, leaves you with the acid salt. So this is the acid salt. of acetic acid. Any acid, I repeat, in vicinity of a base will pull off the H and form the acid salt again. We have a C2 acid, acetic acid, strong base, pulls it off, and the OH and the H form water, and we end up with the acid salt again. Doesn't matter whether it's acetic acid or benzoic acid, you still end up with the acid salt. Okay, to name a carboxylic acid salt, we first name the cation that's part of the base. In this case, it's going to be sodium. And now we're going to, since this is benzoic acid, it's coupling to, we're going to go benzo 8. 8 is the acid salt. So we have the cation base, case is sodium, or frequently it's sodium or potassium, just like 98% of the time it's sodium or potassium. So we've got sodium, and then benzoic acid is the base, but because we've pulled off the H, it becomes a benzoic 8. Okay, because of this guy being extremely polar, they're soluble in water, unless this gets super long, then they are not soluble in water. C6 is the dividing line. Okay, the sodium, potassium salts of long-chain fatty acids are used as soaps. And we've already made soap in lab, and we were using uh, sodium hydroxide, lye. The diatomic and monoatomic cations are used as food preservative. Same with sodium benzoate, extremely common preservative. Okay, so this stuff is used all over the place. Citric acid, all of you have heard of citric acid. It's a nice antioxidant, and it's a triprotic acid, meaning there are 3 groups that are acidic groups on citric acid. Okay, now, when you mix an acid plus alcohol, now remember, Unit 2, we talked about an aldehyde or ketone plus an alcohol. Now we're talking about an acid plus an alcohol. So we've got 2 parts. We've got the acidic part, and we've got the alcohol part. Esters are found everywhere biochemically, everywhere. They're extremely ubiquitous, extremely ubiquitous. Okay, esterification is a process of forming an ester. Okay, that means we need an acid and an alcohol. So we have the acid part in yellow and the alcohol part in kind of an orange highlighter. Okay, so we have butanoic acid, butanoic, and that means it's a C4 acid. Ethyl alcohol is a two-carbon alcohol. We form ethyl for the alcohol, and then the butano O8 as the acid. Salicylic acid, which we'll be using to make aspirin, is interesting because it's both an alcohol and an acid. When we react it with methyl alcohol, it reacts with the acidic part of salicylic acid, not the alcohol part of salicylic acid, and forms methyl salicylate, and that is oil of wintergreen. Okay, so if you remember, when we form an ester, there are three ways to form an ester. There is the alcohol, excuse me, let me just back up here. There's the acid plus the alcohol. Method one. Method two is the acid chloride plus the alcohol. Method three is the anhydride plus the alcohol is the ester. Three ways to form a ester. You need to know this. Test time. Okay. I'm going to ask you, I'm going to give you an ester. I'm going to ask you, what are the three ways to make this? And you're going to go through showing me the acid and alcohol way, the acid chloride and alcohol way, and the anhydride and alcohol way. Okay, so this is the acid chloride way. Okay, so basically, when we look at the acid chloride, we're replacing the Cl, we're replacing the, excuse me, the OH with a CH, with a, we're replacing the OH with a Cl. So this was the OH from the acid. Okay, and here's a good old alcohol. Okay, so the deal is, this is very unstable. And this is much more stable. So this is a very high yield reaction. The anhydride is moderately unstable. So this gives a stable ester. So this is medium yield. And then there is then the third one is where we have just the plain old acid plus alcohol. And that gives us the ester, which is going to be RCOOH, O, R prime. And this is going to be the lowest yield. So you need to know these three. So we've got the acid, we've got the secondary backbone, okay, we're not doing plastics because this is an allied health class. Okay, naming esters. Okay, there are a number of parts of an ester. There is the alcohol part, there's the acid part, and then we're going to combine these two together. So the first part you name is the alcohol part. Second name is the acidic part. So let's look at this example here. And the acidic part, you put O8. Okay, so let's look at this. All right, so we have an alcohol or a acid part, and we've got an alcohol part. So let's put these together. So we're going to go methyl. Okay. So it's going to be methyl. Oh, I'm having my troubles today. Methyl, and this is a 2-carbon acid, so it's going to be etho no 8. So this means it's an ester with this. Now, we also talked about the acid salt named O8 as well. So if it's got a methyl group out front, that means it's an ester. If it's got a sodium or potassium, it's a acid, or it's a acid salt. Okay, so here we are. We have phenol. And we have a 1, 2, 3, 4. So that's a butanoate. 3 parts again. Okay, so esters can form and esters can come apart. So under acidic conditions, they'll form their original acid and their original alcohol. Now, importantly, this happens in the small intestines. And the enzyme to do that is called lipase. Okay, so we have acid part, acid part, alcohol part, alcohol part. Now, under alkaline conditions or basic conditions, it also happens, only it's a different name. It's called saponification. Um, Saponification is when we end up with the acid salt and the alcohol. So this is the acid. And this is what happens when we make soap. We saponify the fat because the fat is an ester. It's a triester called a triglyceride. So if we take this ester, we have acid part, alcohol part in a alkaline or basic environment. We end up with the acid salt and the alcohol. Now, this is the mechanism that we're not going to cover in this class. If you're interested in how the little electrons move around and everything, this is your cup of tea. It's called mechanisms. Okay, so this is the flow chart. We have an acid, carboxylic acid or organic acid. In water, it disassociates. That means that the H comes off. In a basic environment, we form the salt. And then I need to make one more little correction here. And there's no reaction. So we have plain water, disassociates, and the plain water is slightly basic. That's why it pulls it off. Okay, excuse me. In a basic environment, the H is pulled off from the acidic group, resulting in a acid salt. So this is an acid salt. And in an acidic environment, there's no reaction. Okay, Carboxylic acid plus an alcohol forms an ester. And in a slightly acidic acid, we form the original acid and the original alcohol. In a base environment, we form the original alcohol plus the acid salt. So those are the reactions to know. These are the fatty acids that you need to know. I'm going to cover this in much more detail as to what all this means. So that's what I wanted to cover today.